What if I was to ask you to add the numbers 1 plus 2 plus 3, etc., all the way to 100? 1 plus 2 plus 3, all the way to 100. Could you do it? Without a calculator?
No.
Without messing up? In under 2 minutes. Have you heard the story? Young Carl Friedrich Gauss, 4th grader, I think he was 4th grade, 3rd or 4th grade, did it in under 2 minutes with no calculator. Back in the 1800s, have you heard the story about how Carl Friedrich Gauss added up the numbers 1 to 100? Have you heard? Tell me you've heard of the man Carl Friedrich Gauss. No, it would be lying to me. Maybe some of you have heard. Okay. Anyway, he's considered one of the greatest 3 mathematicians of all time, probably. He was in Germany in the 1800s. He was 3rd or 4th grade, and they had slates back then. Remember the little handheld chalkboards, little slate boards? All the students had little slate boards in their little classroom, and the teacher, I think honestly, the teacher was just sick of dealing with the kids and just wanted, some free time, which happens sometimes, doesn't it? In the elementary school classroom. Sometimes there's busyness activities that may or may not be all that profitable. So the teacher said, add up the numbers 1 to 100 on your slates. Go. And so all the kids were supposed to, you imagine doing that on your slates? 1 plus 2, 3. And then add 3, 6. And then add 4, 10. Now we add 5, 15. Add 6, 21. Add 7. Okay, we're going pretty quick here. So add 8, and then you start getting harder. What's that, 16? 36. Add 9, 45. Add 10, 55. And actually, they'd have to keep erasing the slate, right? Because it'd be full at that point. I'm at 55, then you have to erase. Start again. With 55, I'm at 10, and I'm already tired. I'm not going to go any further. So, all the way to 100. Anybody seen this? Anybody know how he did it?
I think I've seen it. There's like a formula where you add like the last one and the first one, and you keep going. There's like a pattern to it. Yeah.
There's a pattern for sure. Yeah, this unit we're in right now, unit number 3, which we're starting now, is all about problem solving. So unit 1 was, what was it about? Oh, about numbers and foreign bases, right? We did that weird base stuff, learning how our base system operates. Unit 2 was all about fractions and decimals and number theory, getting all that straight, right? Factors and GCF and LCM. This 3rd section is all about problem solving. How do you solve word problems? How do you attack problems? This is probably the most valuable for future little engineers and scientists that are going to be sitting in your classrooms, is how to think about difficult problems. How to come in when it's not just straight ahead, step 1, step 2, step 3, there's your answer. Instead, to come in and kind of think logically and how you attack a problem and reason your way through it. Yeah, so there's a pattern here. So the reason I say all this because you're hitting right on the money. Math is totally patterns. I mean, somebody was to ask me one word, what is math about? Well, maybe 3 words. It's the science of patterns. I mean, what is math? In the end, what is math? This thing we call math is patterns. It's getting better. And then the more you study math and grow in math ability, what you want to give those little kiddos is not adding, subtracting. I mean, yeah, they should learn to add, subtract, multiply, and divide. Not that that doesn't matter. But more and more, the ability to deal well with patterns. To see them, predict them, describe them, pattern thinking. That's what math trains in an individual, is the ability to deal well with patterns. So let's look at this. There's a pattern here. So it's something like you're saying. You said first number with last number.
Yeah, and then like you could keep going in. So it's like 101. I don't know.
Yeah.
It's a formula.
Right. So you're saying add the first number. Here, let me do it. Well, I'll tell you what Gauss basically did. What you're saying. How about if I just put the last number right here? Gauss thought exactly what you're saying. How about if I just reverse the list? Why don't I just try something? Do you remember Einstein's? Einstein's the one that came up with the fact that everything travels relative to the speed of light the same. I don't know if that has any meaning for you. The theory of relativity in physics, right? And he's quoted as saying, for a scientist, sometimes imagination is more important than knowledge. What did he mean? Sometimes you just try stuff. You just give it a shot, and something works out. That's what Gauss basically did with this. He just said, I don't know. He didn't feel like sitting there at his slate board and adding the numbers 1 to 100. So he said, maybe I'll just reverse the numbers down below. Maybe I'll just put them reversed like this, down below. 3, 2, 1, right? And then, like you're saying, add those up. What if I add them straight up and down here? What's 1 plus 100? 101. And then plus 99 and 2? 101. And 98 and 3? Okay, yeah, great. That's cute and all. So it comes out to be 1. Does it keep going all the way? It looks like it does. Yeah. 101. 101. 101. Okay, yeah. Neato. So what? No. Answer to the whole problem. Do you see it? Not just a cute little pattern. Math is patterns, but in patterns is power. That's what science is. Noticing the pattern of how gravity works. Noticing the pattern of how air flight works. Noticing the pattern of how electricity works. And thus we're able to fly through the air and power buildings. It's all patterns. Patterns are power. What do I mean? We have the power to answer this question in 2 seconds now. Why? Why is that pattern so powerful? Well, how many 101s are there?
50.
Right in the end. Right now, how many 101s are there? How many 101s are up there?
On the screen?
On the screen. How many 101s are implied with the dot, dot, dot? There's 1 underneath the 1. There's 1 underneath the 2. There's 1 underneath the 3, etc. There's 1 underneath the 98, 1 underneath the 99, and 1 underneath the 100. How many 101s are up there? 100. So what do all these 101s added up? What do they add up to? How many 101s are we adding up? So what's the quick way to add up 101 100 times? Take 100 times 101. But that's the list twice, isn't it? Right? We did the list forward, and then we did the list backwards, and got these 101s. So that's the list twice, isn't it? So what do I got to do to fix it? Because I only want the total once, not twice. What do? Divide by? Yeah. Done. In fact, we can work that out real quick. What's 100 divided by 2? We don't even need a calculator. 50 times 101. Now, how do you multiply? You don't need a calculator for that. Just forget about the 0 for a minute. What's 5 times 101? 505, right? And then put the 0 back on, tag it at the end. 5,050. Well, the story goes, Gauss whipped it out that quick, brought it up to the teacher, who was trying to buy time from the little whippersnappers and try to get some spare moments, and Gauss comes up with the answer right away, and supposedly got accused of cheating and sat in the corner of the room for the rest of the time. But Gauss went on to greatness after that. I think the biographies are interesting math. So Gauss went on to do many other great things, and his dad was a bricklayer. This is Germany in the 1800s. His dad was a bricklayer, and his dad wanted him to take over the bricklaying business. Good thing he didn't. Gauss, the village was like, no way. Gauss is a genius. They saw his genius early on. So the village pooled their money together, sent Gauss away to the university in Germany there, based on the village money. And Gauss would quickly be ahead of his professors. So that'd be like if you had classes here and you had a student that was in the class that would quickly be ahead of the professor. Like if somebody right away in here was like pointing out things that I'd never seen before and figuring out math things. Gauss did that quickly at the university and quickly graduated and went on to amazing status as a mathematician, scientist, philosopher. They did everything back then. It's funny, we're so specialized now. Gauss did astronomy, physics, did some chemistry, did some statistics, did number theory. Now we're all specialized, right? we have the doctor of the left pinky finger only. And things that's exaggeration, but you know what I mean. It's different back then. Anyway, so all right. So you see that method? See how we can do it by just reversing that list with that technique. We see a pattern, and then we can quickly say, well, there's 100 over 2. There's 50 101s, so the total must be 50-50. So can we use that now? So the question is, why is my screen blank? Let me get the thing up there for you. Let's try that. Let's add the numbers 1 to 102. Try the same technique. Notice I didn't give you a formula. I just gave you a pattern. So 1, 2, 3, 4, ... up to 102. So can you do that to get however you want? However you want. On your own paper. All right, so the first one, 1, 2, 3, 4, ... 102.
Yeah.
You know what I would think would be really easy?
Probably what I did.
What'd you do?
I just took the answer from the first one and then added 101 and then added 102.
Beautiful. I'm with you. Cammie, that's exactly what I thought, right? I mean, this is the numbers. Isn't this just the numbers 1 to 100, right? The ... means, you know, all the numbers, plus 101 plus 102.
Yeah.
And we just did 1 to 100. It was 50-50,
Yeah.
right? Plus 101 plus 102. That's fine. Want to just do it that way? Almost seems like cheating, but it's never cheating. If you've observed a pattern, it's called mathematical thinking, right? And so, let me see, I can almost do that in my head. 5, 2, 5, 3?
Yeah.
5, 2, 5, 3. See how easy that is? Now, in case you still feel like it's cheating, I'll do it the longer way too. But, right, because we already did 1 to 100. That was 50-50, right? We just did it right here. Right, 1 to 100 came out 50-50, and then this just adds 101 and 102 to the end, doesn't it? So just take 50-50, add 101 and 102 to the end.
We can do the same thing with you.
What's that?
We can do the same thing. Oh, no, never mind. We can't. Never mind.
No, the next one's odd, so we're going to have to be more tricky. My little gimmicks aren't going to work on the next one. But yeah, but I'll do it the long way too, in case that bugs you. I'll do the long way. 1, 2, 3, all the way to 102. And then down below, what was Gauss's method? Down below, write it backwards, right? So 102, 101, 100, all the way down to 1, right? And then add them vertically. And that's 103 and 103. See, that's the trick. They all came out the same, huh? 103, 103. So a whole bunch of 103s. The question always is, though, how many 103s? How, right? It's a whole bunch of 103s added up. How many 103s? Well, 1 for each of these numbers up here. Right? Is everybody tracking with me on that? This number, this number, this number, all the way to 102. Each of them points to a 103, doesn't it? In higher math, we call that a one-to-one correspondence. There's a one-to-one matchup between the numbers up here and the 103s down below. There's a one-to-one matchup, which means however many of these there are, there's the same number of 103s. So how many 103s are there? 102, right? 102 103s, but you got to divide by 2 because that's the list twice, forward and backwards, right? So calculators at 52, 53? That's what we got, right? Yeah. Anyway, so there it is. Let's do the part B now. So part B is 103 all the way to 103. Okay. So part B, 1, 3, 5, ... all the way to 103. And then, did you try the list backwards thing?
No, you have to do only the odd numbers.
Right. Yeah, that's all that's in there is odd numbers. Yeah, so when I say the list backwards, I mean that list, and that list only has odd numbers. Yeah, exactly. So that'd be 101, 99, ... down to 1. We good? That is the list. The list is only odd numbers, huh? So that's the list backwards. And then add them vertically. So I'll add them up, and then this is going to be 104. This is going to be 104. This is going to be 104, etc. They're all 104. Now, here's the big question. How many 104s are there? We know it's a bunch of 104s. How many 104s are there? How are you coming up with that?
I divided 103 by 2.
Yeah. It's like if you take that 103 and you divide it by 2, you get, what is it, 51.5? So it's like, hey, what does that mean? Are there 51 of those things, or are there 52 of those things? This is what you're going to face when you take Math 100. And there's going to be no canned formulas. There's going to be no, like, in this situation, always round up. They're not going to do that for you. They're going to expect you to be an independent thinker. Now, what do I mean? How do you become and nobody told me this rule. That's exactly it. We look, what is mathematical thinking? Pattern thinking. It's pattern thinking. So think about the question that's before you. You're wondering, when you have a whole bunch of odd numbers, and you want to know how many there are, right? Isn't that the question we're saying? From 1 to 103 is a bunch of odd numbers. And I want to know how many there are. Can I just take the last odd number and divide it by 2, and that'll tell me how many there are? Well, no, it comes out decimal. Okay, so did you round it up or round it down? Remember what I've encouraged you to do when you're dealing with a hard question?
Simplify it.
Make it simpler. Test it out and apply it to the harder situation. Australia?
Why do you divide it by 2?
Because we're skipping half the numbers, aren't we? When you do odd numbers, you're skipping half the numbers. 1 through, we skipped 2, skipped 4, skipped 6. We're skipping half the numbers.
So whatever that you skip, that's what you will divide it by.
Well, that's what we're testing. That's what we want to figure out. So let me show you how I would do. So I don't, honestly, I don't, being a math science person does not mean you walk around with your head like a catalog full of all these dumb facts. I don't walk around going, yes, I always know that if you're adding up a bunch of odd numbers, you always have to round that number out. No, I don't know. That'd be dumb to know that anyway. What a dumb thing to know. Instead, what it means to be a math science person is you have the ability to describe a pattern and test your philosophy. You have the ability to test it. Now, what do I mean test it? Well, it goes all the way to 103. That's hard. How about if I just go to like 5 and test the principle? I know how many numbers there are 1 to 5. There's 3 numbers. Clearly, I'm looking at them. So what was the philosophy? See, this is where you got to be really clear on your hypothesis, if you will, if you want to use a science term. What is our theory? We take the last number and we do what with it? Divide it by 2. So if I take the last number and I divide it by 2, what do I get? 2.5. So you tell me. Do I round that up or round that down to get the real amount of numbers there?
You got it up.
You got to round it up. It's got to go up to 3. So what's the real true rule then? What's the pattern? Round it up. See how that makes you 100% confident? See how quick and easy that was? Right? You don't have to walk around with a catalog head full of facts. You just have to have the ability to test your own theories. You see what I just looked at the pattern and said, I have no idea. So I'll just take this, divide by 2. Oh, I know there's 3 numbers there. Must be round up. I guess it's round up. So round it up. There must be 52 numbers there. So there must be 52 103s, huh? But that's the list twice. Oh, 104s. Thank you. Yeah, these are all 104s. They're not 103s. I'm getting lost in my own work here. Yeah, there must be 52 104s. Everybody see what I'm doing? We tested out the philosophy that if you have a bunch of odd numbers, you take the last one, divide by 2. If you round that up, you'll get how many numbers were there. So if I take the last number, 103, divided by 2, and then round that up, 52, that's a bad-looking 2. 52 numbers must be there. So there must be 52 104s, but that's the list twice, so divide by 2. That's the list forward and backwards, and then hit the buttons on the calculator. Somebody got that?
2704.
2704. Those numbers must add up to 2704. So you can have confidence with that because you tested your own philosophy, saw what was true, and applied it. It's not guessing, and it's not hard either. I didn't have to do big fancy numbers. I didn't have to have a great memory. I have a terrible memory. I've told you I always kid my wife, right? She'll remember things. She has an amazing memory. She'll remember things. You know, we've been married 27 years, I think. See, I don't even know that. I think it's 27. Anyway, I should know that, huh? Once I pass 25, I lose track. And she'll remember some trip we took way back when and what we had for lunch. I always say to her, honey, it's like you're already a widow. Your memories are your own. I don't even remember the trip. Anyway, so I could have never made it in math and science. It was about having a good memory. It's not. It's about just being able to problem solve. So everybody see the idea there on that? That's what we're going to do on all these problems, is test our own philosophies. I better get moving. I'm being too long-winded. Any questions on that one? Simon?
Didn't you just so you had the pattern 1 through 5?
Right.
So there's 1 through 5, 7, 9.
Yeah.
So there'd be 5 in each group between 1 and 10. So could you just do 5 and then multiply that by 10? Because each group 1 through 5, 7, 9, and then 11, 13, 15, 17, 19. So
1 through
5 times 10, and then add 2, which would be 1, 1, 1, 3, which would be 52.
15. So, okay, I'm trying to track with your patterns. So you're saying 1 through 5, 7, 9, 5 of them in the first 10, then do the next one and keep going.
You get to 100, and then there'd be 10.
So the last one would be, what would it be? You're saying 91, etc. 91, 93, 95, 97, 99.
Yeah.
Okay, and then what?
And then you multiply 10 groups of 5, and that'd be 50. And then just add 1 and 1 and 1 and 3, and that'd be 52.
Oh, nice. I like your thinking. Yeah, so you see what Simon observed? He looked at it a different way. He's saying, look, there's 5 numbers in that group. You know, a 1 to 10, basically, stopping it. 5 odd numbers in that group, 5 odd numbers in the and the next one would be 21, 23, 25, 27, 20. It's going to be 5 numbers. There are 5 odd numbers in every 10. He's basically observing, right? And these go the 10s, 20s, 30s, 40s, 9. There's 10 groups there. So he's saying, look, there's 10 groups of 5. That's 50 numbers, and then we had a 101 and a 103. So add 2, there must be 52 numbers. Nice. Great. Yeah, there's a million ways to go after it. I like that we had another way. Yeah, it's not just my way. That's a great pattern Simon observed there. That is mathematical thinking. Just looking for some pattern. Any pattern you find, that's it. That's what makes a scientist. That's what makes an engineer. That's what makes somebody that can do STEM. It's developing that kind of thinking, the ability to see, observe, predict, describe patterns. That's mathematically. And that's valuable in more than just math, isn't it? What does a doctor do? Looks for patterns and symptoms. What does a lawyer do? Looks for patterns in the law. They call that precedent, right? That's what a lot of fields do, is they deal with patterns. Math trains you to deal. That's what you want to do for those youngins more than anything else. In math time, it's make them pattern thinkers. That's so much more valuable. I mean, we have calculators to do the numbers. I mean, I know you got to teach them to add, subtract, multiply, divide. But really, that's not as important as being able to describe, predict patterns. Cookies are sold, so let me rewrite it. So if cookies are sold in 1 at a time, 8 at a time, or was it 12 or 24? 24 at a time. 24 per package or whatever. Bless you. Per package. So how many ways to get 48 cookies? Is that what we're talking about? To buy 48 cookies. Right. Okay, same thing. So basically, so if there's 3 different kinds of ways to get cookies, you can get them 1 at a time. You can get them in packages of 8 or packages of 24, 2 dozen. Then how many different ways are there to get 48 cookies? What do you say? I'm going to go there and I'm going to buy 48 cookies. How many total different ways could you buy 48 cookies? What we're going for now is making a systematically. This is, by the way, how you need to think if you're going to do problem of the week number 1, the proof is in the pudding. You need to list with a system all the ways that 3 numbers can multiply to be 72. So in this question, we're going to list with a system all the ways you can have 48 cookies. The reason we must have a system is because that way we know we didn't miss any. The whole point is that you don't miss any of the ways. So let me just give you one system about what. You could start, here's one system. There's a million different systems. The system I'm going to use is start with the biggest first. The biggest packages possible. You can read, sorry, I'm writing fast and scribbling. Can you read that? Biggest packages possible. biggest packages possible. All right, so if you're going to get 48 cookies, what's the way you could do it in the biggest packages possible? Yeah, 24 in a 24 pack. That's one way you could get 48 cookies. Next, let's have another way that has less big packages. Well, you could have the first 24, and now what's the next biggest way? 3/8. That's next. You see how I'm using a system, so I know there's nothing between those two. I'm not missing anything. That's the next biggest way. There's other systems. You could have started with the smallest or all kinds of different systems. So what's the next biggest way? 24, 8. What could I do with that last 8?
8 ones.
Yeah, I'm just going to write 1, 1, 1. Well, what am I going to write? 4, 5, 6, 7, 8. There we go. 8 ones, huh? That's still 48 cookies, isn't it? It's a different way to get 48 cookies. What's the next way? Both these are 1, 1. And, right? You break both those 8s into individual cookies. You get the pattern, right? Next one, all 3 8s. See what I'm doing? Do you see the system there? We're not done yet, but do you see the pattern I'm following? So I broke the 24 into 8s, and then the 8s one at a time into individuals. Is that good? Okay. Now, where am I going to go from here? There's 5 different ways so far. They want how many ways? The answer is going to be how many different ways. So far we have 5 different ways. Now what else can I do?
Break up that 24.
Yeah, now I can start breaking up that 24, can't I? So if I'm going to break up that 24 into 3 8, so let's go, and I'm going to go back. I'm going to go back to, well, if I went to step 1 and I broke the first 24 into 3 8s with the 24 at the back, that's not any different than number 2. That's the same thing as number 2. So I'm not going to list that one, right? But instead, I will have, 6 8s, huh? So that's the next biggest way. Is everybody tracking with me? So I had the 2 24s, and these are all the ways having 1 24. See my system? I had 2 24s, and then from cases 2 through 5 are all the ways to have 1 24 instead of 2 24s. If you have 1 24, then you can have 3 8s, 2 8s, and individuals, 1 8 and individuals are all individuals. Those are all the ways to have 1 24. So 2 24s, 1 24, now no 20. Now I'm going to begin to list all the ways to have no 24 packages, no 2 dozen packages. See the system I'm using? So you could have all 8s, or what comes next? You break one of those 8s into individuals, huh? So I have the first, how many 8s are there? 6 8s? 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7, 8. And then next, 8, 8, 8, 8. And then can I just go 1s and 1s? How about I just do that? I'll just put a 1. We know it means 8 1s. 9th case, 8, 8, 8, 1, 1, 1. 10th case, 8, 8, 1, 1, 1, 1. 11th case, 8, 1, 1, 1, 1, 1. 12th case, all 48 individual cookies. See how I used a system? I know I got them all. Right? This is the only way to have 2 24s. These are all the ways to have 1 24. And this, from 6 on down, is all the ways they have no 24s, all 8s, or 5 8s, 4 8s, 3 8s, 2 8s, 1 8, no 8. So there's 12 different ways. There's 12 different ways you could order those. So that's a systematic list. There are times when you're solving real-life problems where you need to have a system to make sure you're not missing anything and can research all possibilities. That's all that is, an exercise in being systematic.
When finding like the smaller packages instead of the biggest ones, where would you use or just the biggest ones?
What's that?
Like instead of like you said the system was biggest packages possible.
Right.
Would you able to do like the smallest two? Like you could do one, like 48 packs of one, or it's just like one individual.
Yeah, that's what this is right here. This is,
Oh,
yeah.
never mind.
Yeah, this means 8. I just started to get lazy, but this is 8 ones, 8 ones. Yeah.
Okay.
No, we could. Yeah, no, that'd be you. When I say my system was biggest package, I meant I started with the biggest
Is it
package.
in there, like-
But you could have started with the smallest
Yeah, okay.
and worked up to bigger and bigger packages. Or there's other things too. You could say I'm going to start with all the ones that have 8s only, and then anyway, there's a million systems. Kathy stood on the middle rung of a ladder. She climbed up 2 rungs, moved down 4, then climbed up 9, then she climbed up the remaining 3 to the top. How many rungs are there in the whole ladder? So let me write those facts out for you. So, stood on the middle. So she starts on the middle. And then she went, what'd she do? Up 2, down 4, up 9. Up 2, down 4, up 9, and then up 3 to the top. And up 3, and she's on the top. How many rungs in the ladder? Okay, so there's the question. How are we going to solve this problem? Draw a diagram. You really have to draw what they're showing. Unless you're just amazing in your head and you can picture all that, we need to draw it. We really need to draw it. So let's start. Kathy starts. I'll just start her right here. This is where she starts. And where does she start? It's the middle rung, huh? They told us that she starts on the middle rung. All right. And then what is she going to do? Up 2. So I'm going to go 1, 2. She starts here and goes up 1, 2. I'm going to literally draw it. And then she goes down 4. So she's going to go here. She'll start here and she's going to go down 1, 2, 3, 4. 3, 4. So down 4. Now she's here. And then she went up 9. So I'm going to go up, starting from here now, up 1, 2, 3, 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. Up 9. And then the last thing, up 3 more. 1, 2, 3, to the top. This one here, oh, and my underline's all getting confusing here. Let me do a better job. So up through, so 1, 2, 3 more. This one must be the top. This one's the top. Good with that? I just traced it out. Now, okay, so what? That's the top. Great, so what? Well, what do they want from me? They want how many rungs on the ladder. Well, can you count how many from here to there? And add the one in the middle, huh? Because if this one's the middle, then whatever is below and above must be the same. That's what it means to be the middle, huh? So how many are here? I'm just going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 here, must be 10 there, 1 in the middle, 10, 1, 10, 21 rungs on the ladder. See how I came up with that? I just mapped out what she was doing. Middle means same amount above and below. 10, 10, and 1 in the middle. 21 rungs must be on that ladder. So that's how you do number 9 and number 10. You just draw a diagram of what they're saying. and then just count them afterwards. That's another problem-solving technique. All right.